Hi, my name is Nabasti Kayat. For today's presentation, I'm going to talk about basic simulation modeling. Specifically, I'll talk about simulation of a single server queuing system. In the real life, there are much more complexity than having a simulation of a single server queuing system. However, when we measure the performance of such kind of system, it will be very easy for us to go for much more complex issues. The content of the presentation is going to be a general overview. Then we state the problem. Then we try to measure all the performances. Then a little bit discussion is going to be presented. With the simulation of a single server queuing system, we will show how to make the simulation. Then it is simple, as we said, but it contains many features found in all simulation modeling. It's very important here to see that the random variables that we are trying here to estimate are all independent, identically distributed, which means that the inter-arrival times have the same probability distribution. The case study for this lecture is going to be the one operator barbershop. This is a single server queuing system representation. So for a single server queuing modeling, we assume the inter-arrival time is going to be A1, A2, A3, and so on. They are all IID random variables, which indicates that the inter-arrival time has the same probability distribution. We also assume that the service time, S1 to S3, S4 and so on, are also IID but are independent from the inter-arrival time. The queuing discipline for this example is going to be first in, first out. Some measures that we will try to conduct, one of them is the expected average number of customers in the queue. Another one is the utilization factor of the service, and the third one is going to be the expected average delay in queue for end customers. We will explain how the simulation process will proceed. So we assume these values, the arrival and the departures are all given. So if you start the simulation at time, let's say at time 0, then the first arrival is going to be at time 0.4. And the second one is going to be, the second arrival is going to be at time 1.6, and he is going to enter the system as soon as let's say the first one has left the system, and so on. So if you with simple math we can get the inter-arrival time. So we subtract the arrival of the second customer from the first customer to get the inter-arrival time for the second customer. We subtract the arrival time of the third customer from the arrival time of the second customer in order to get the inter-arrival time of the second customer. Another given data is going to be the service time, the time that takes from the customer to take the service. For instance, here we can see that the first customer is going to enter into the system at time 2, while the second one, the first customer is going to need 2 minutes to complete the service, while the second one is going to need only 0.7 minutes to have the service done. And the third one is going to need only 2 minutes to 1.2 minutes to have the service completed, and so on. So we have 2 types of events here, arrival and departure. So we draw a graph for this. Let's draw a line here, assuming that the simulation begins at time equal to 0. So the first arrival is going to be at time 0.4. The next event, which is another arrival, is going to be at time 1.6. So A1 denotes the arrival of customer number 1, A2 denotes the arrival of customer number 3, and according to the data if you can see it, arrival occurs at time 0.4, 1.6, 2.1, 3.8, and so on. So we have now 3 customers have entered into the system. So the departure of the first customer is going to be at 2.4, and this will be denoted at D1. Okay, so after 2.4, if you look at the arrival times, after 2.4 there will be 3.1. So the 3.1 is the departure of the second customer. If you look at the D1, when the first customer departs, then there will be only 2 customers left in the system. One is served and the other one is going to be in the queue. When the second one departs, we will only have customer number 3 in the system. When the third one departs, then there will be no one in the system, and the server is going to be idle from 3.3 to 3.8. Then another event is going to occur at 3.8 when the fourth customer enters into the system and he sees that the server is idle. He gets into the service immediately. Okay. Then another customer is going to join this the system at 4, but he has to wait because customer number 4 has not left yet. Then when the customer number 4 leaves at 4.9, then customer number 5 is going to enter into the service at 4.9. Then there will be another arrival at 5.6, then another arrival at 5.8, then the 8th customer will arrive at 7.2, then customer number 5 is going to complete the service and leaves. Why? Because the customer number 5 will need 3.7 minutes for the service to be completed. And now let's see how number of people in the queue is going to change. So if we take the vertical axis as a QT, denoted as the QT is the number of people in the queue at time t. Okay, with a number of persons in the queue, 1, 2, we put 1, 2, and 3. So we can see that from t equal to 0 to 0.4, there will be no customer and there is no queue. Even from A1, when A1 enters into the system, again there will be no queue because he is going to join the service immediately. However, when customer number 2 enters into the system, he sees that A1 is already in the service, so he needs to wait. So the number of people in the queue is going to raise to 1. Then, customer number 2 is in the queue only, so number of people in the queue is 1. Then when customer number 3 arrives at 2.1, then he also will join the queue, and the number of people in the queue is going to be 2 until the first departure occurs at 2.4. Then the second customer enters into the service. Only A3, customer number 3, stays in the queue, and that's why the number of people in the queue is going to be 0. There's going to be 1. Then when the third customer also leaves at D3, then there will be no people in the queue. So the queue is going to be 0, and the system is going to be idle until the arrival of the fourth customer. Again, when he sees that the service is idle, he joins the service immediately, and there will be no queue. Queue is equal to 0. But when customer number 5 enters into the system, he has to wait for the customer number 4 to finish, and that's why the number of queue is going to be 1. And at the same manner, we can see the others. For instance, when customer number 6 enters, he sees that customer number 4 is in the system, and that's why he has to wait until he gets his turn. So number of queue is going to be only 1. But then he is in the system, customer number 6, and he is in the queue. Customer number 7 also enters into the system. He also will be in the queue, so number of queue is going to be 2. Customer number 8 enters into the system, number of queue is going to be 3. So there will be a stopping condition here when there is customer number 6 and the number of queue are equal to 3. So that's how we can explain a single server queuing system. Then we can perform some measures to get the expected number of expected average number of people in the queue, expected average number of minutes of delay, expected average service utilization, server utilization, and so on. So the area under the histogram here is the integral of the number of queue, the expected average number of queue in the system. So it is very easy to calculate. We will have, we can see from the histogram here we have 3 cases. One case is when the number of people in the queue are 1, and the second case is when the number of people in the queue are 2, and another case is when the number of people in the queue is 3. So for the first one, number of people in the queue is 1, so we will have 4 cases from 0.4 to 1.6, from 1.6 to 2.1, from 2.4 to 3.1, from 4 to 4.9, from 5.6 to 5.8. So we will make subtractions. We will get these numbers. Then for the second one, we only have, which means number of people in the queue are equal to 2. We only have 2 cases, is from 2.1 to 0.4 and from 5.8 to 7.2. So you will subtract 7.2 from 5.8 from 7.2, add it to the subtraction of 2.1 minus 2.4. Then for the third one, I mean number of people in the queue, if it is equal to 3, we will only have one case, which is between D5 and A8, 8.6 minus 7.2. So we get 9.9. So this figure, we can get the expected average number of people in the queue is going to be equal to 9.9 over 8.6. As for the utilization factor of the server, where we can see that the random variable, the demi variable b of t is going to be equal to 1 if the server is busy and equal to 0 if the server is idle. So we can see that we have only two cases when the server is idle, is from time equal to 0 to time equal to 0.4, and from time equal to 3.3 to time equal to 3.8. The rest, the server is going to be busy. So we can see from 0.4 to 3.3, the server is going to be busy, and from 3.8 to 8.6, the server is also going to be busy. So how we can calculate utilization? By subtracting these two ranges and then adding them up, we're going to get 7.7 minutes. So the percentage of the server getting busy is going to be that 7.7 upon 8.6. This is the total number of minutes of the system. Now we would like to compute the delay. So how we compute it? We can see that the first customer is not going to face any kind of delay because he is going to enter into the system immediately, and there will be 0 delay. For the second customer who enters, he will only be served when the first customer departs. So this is going to be the difference between D1 and A2. So D1 minus A2. For the third one, when he enters into the system, he will be served once the second customer departed. So the delay is going to be the time difference between the departure of the second customer and the arrival of the third one, and so on. So we calculate all of these differences of the minutes, and we get the sum. which is the total delay 5.7 minutes. Then the average delay is going to be 5.7 minutes by number of people who are in the system. Actually, as we said, the simulation is going to be ended when number of people is equal to 6. Then some inputs that we need to take into consideration and see the properties of them. So the average delay in the queue is going to be a discrete time statistics, while the time average number of customers in the queue and the proportion of time of the server is going to be busy will be continuous time statistics. So in simulation, as we know that both of discrete time and continuous time statistics are common in simulation. Possible measures other than the one that we already talked about: average delay, average waiting time, average queuing length, then the average system size, then system utilization. That's all for today, and thank you very much.